Hey guys, I hope you're doing well. This is the second lesson from Unit 4. This one's going to extend on our first one, which was about probability distributions. Before we get into it, let's just do a little warm-up. So if you want to, you can try this yourself. So you'll need to press pause and then give it a shot and see how you do. Otherwise, you can follow along. So this one says the school lottery has 5,000 tickets for sale. There's one grand prize of $2,000. And then 5 second prizes of $100. It says, what's the expected value of the lottery? So they're talking about the values. So basically, how much is going to come out per ticket on average? So what we need to do is we say our expected value, so always E of X, is going to be the value of each of the outcomes. So one outcome is the $2,000. And the probability that that's going to happen, because there's only one, and there's a total number of 5,000 tickets sold, I have 2,000 times 1 over 5,000. And then my second prize, I've got 5 of them, and the value of them is 100, so I have 100 times 5 over 5,000. So pretty easy math to put together, so I end up with 2,500 over 5,000, which is the same as 0.5. I'm going to put an extra 0 there because what this means is that this is the expected value or payout of this lottery. So therefore, the expected payout of this lottery is 50 cents, basically. And so if you were playing this, you would expect if you were to buy, on average, lots of tickets, your payout would be this. And in fact, if you bought all the tickets, this is how much you would get back per ticket on average. So the second one says, let's say you buy a ticket for, if you buy a ticket for $1, what's your expected profit for per ticket? So this is assuming you were the one who's going to make the money here. So I've got my profit is going to be $1 minus my expected value. So I've got $1 here minus the 50 cents. And so I'd be expecting to make about 50 cents per ticket. So therefore, the profit per ticket is 50 cents. So if you were trying to figure out how much you're actually going to make on this lottery, then you're going to make 50 cents times your 5,000 tickets, which is going to be $2,500. Okay, so today's lesson we're going to look at one example of the type of probability distribution, and we kind of talked about this briefly last class, and that's what's called a uniform probability distribution. And in this case, every outcome has an equal probability of occurring. So each outcome, whatever the chance is, each outcome is going to have the same amount. And so there's a few examples like this, but one simple one would be tossing a coin. So if I have my outcomes, so remember your probability distribution can be in a table or a graph, or both. So my outcomes here would be a head versus tail. And my probability, if I call the outcomes X, my probability of each is going to be 1/2. So anytime you get the same or equal probability, that means that it's a uniform probability distribution. So if I represent this in a graph form, I always have my probability on the y-axis. There's my cat. And on my x-axis is always going to be X, or the outcomes. And so pretty easy, I'll just make a little bar graph here, or histogram. So I've got my heads and my tails. And it doesn't matter really where you put your probability because they're all going to be the same. So I'll put my 1/2 there. Ruler is always best, but I can't use that here with my iPad. So I've got both being equal, like that. And so there's my probability distribution for that uniform example. So one thing to note, in all of these cases, even if it's not uniform, my probability total should always be 1. I should always have 100% of my probability or of my outcomes, so that should always be 1. So on the bottom here, it just says this is a uniform probability distribution. And so definitely the easiest of the probability distributions that we're going to look at. And there's a few advantages if you recognize that it's a probability distribution that's going to be uniform. So one of those is that the expected value can be simplified slightly in that I don't have to go through and multiply by each of the different probabilities because I know the probability is going to be the same. So I can say my expected value is equal to whatever the probability is times all of the outcomes added together. So these are my outcomes or the values of whatever I'm talking about for my situation. So if we look at this example here below, it says a spinner which has 8 equal sections. So seeing this, I know that they have equal probability that I'm going to land on any of those 8 sections. And those sections are numbered 1 to 8. And if the spinner lands on a prime number, so I've given you what the prime numbers are, so 2, 3, 5, 7, the player wins 3 tokens. If the spinner lands on a composite number, which is 4, 6, and 8, they lose 3 tokens. And then if the spinner lands on an identity number, which is just number 1, the player wins 5 tokens. So if we think of our outcome, so outcomes here are going to be 1 through 8. And you can think of these, again, the probability is all going to be the same because I've got equal opportunity for each. So I'm just going to fill it in like that. It's all going to be the exact same anyway. And then the win-loss is like the value. So I'm just going to put in brackets here. This is my value that I'm concerned with. And this is like, in my formula, this would be the f of n. So if I get a 1, this is if I get 5 tokens. So I'm going to put 5 here. And if I get a 2, 3, 5, or 7, I win 3 tokens. So I'll put 3, so 2, 3, 5, and 7. And then for the other example, I lose 3 for 4, a 6, and an 8. Oops, that should be minus 3. Like that. So these are the values that I'm concerned with, and those are what's going to determine what my expected value is if I was to play this game over and over. And so when I come up with the formula here, the expected value, I take the probability, so P of X, and I multiply it by all of those different outcomes until I get all of my outcomes. So if I do that, I go 1 over 8. And then I simply take all these values and put them together. And put a plus 7 there. That should be 3. And if I do that, then I add up all of those values. I only have to multiply it by 1 probability because it's going to be the same. So if I add them up, I should get 8. Pretty sure that's right. And then if I multiply that by 1 over 8, that's easy. That just becomes 1. So what that means is, therefore, the expected value, or the expected number of tokens, per spin is 1. So if you were to play this over and over, you would expect that you would get 1 token. So in this game, they have to give up, if we look at C, you have to give up 1 token to play. And then the question is this a fair game? So before we said the expected value should be 0, and that's if there's no price to pay the actual game. But let's say you're expected to win 1 value or 1 token coming out of it, but you also have to pay 1 token. In that case, they kind of offset each other, so we know that the expected value is equal to the price. And so this is 1 equals 1, and therefore we would say it is a fair game because you have equal chance of winning and losing over the long run. So therefore, yes, it is a fair game because the cost is equal to the expected value. So again, because I know my price is equal to what my payout is, I can say that it's a fair game. Okay, so hopefully that's okay. It's a rather quick lesson. Here are the practice questions listed on the bottom. Some of them get a bit trickier than those, but I think it's good to always challenge yourself in the practice anyway. If you have any questions, of course, let me know. Take care.